Okay, this is the beginning of a new topic, momentum. And this is the first of at least two charts on an overview of momentum. So a couple of larger points that need to be made. First of all, and perhaps most importantly, momentum is a vector. P is usually the letter that we use for momentum, and momentum is for a point mass is simply the mass of the particle times its velocity. And so, for example, if you had a mass that was 2 kilograms and it had a velocity of 3 meters per second in the I-hat direction, its momentum would be this vector P of 6 kilogram meters per second in the I-hat direction. The product, in other words, of the 2 kilogram mass and the 3 meter per second I-hat vector. Second point is that we know from previous work that F net is equal to ma. That's Newton number 2. And a more general way to state that law is that the net force is equal to the rate of change of momentum. It's equal to delta P over delta T. And so I have a little vector picture over here. Again, just think of a point mass, and let's say that a point mass has at time t a velocity p, a momentum p, in this as indicated by this first vector. And then at some later time it has a momentum p of t plus delta t. And in that case, delta p would be this vector right here. P of t plus delta p is equal to p of t plus delta t. And so this would be the change vector for the momentum, and this, according to this second statement of Newton number 2, the net force would be in that same direction. In words, net force acting on mass m is equal to the rate of change of momentum. Thirdly, for a system of masses, and so imagine that we have several masses, 2 or more. If the external force is equal to 0, then the sum of the momenta of all the masses, which is going to be equal to the total momentum, will be constant. In words, if there are no external forces, total momentum is conserved. And a special case of this is that the external force in a particular component direction is 0. So, for example, if the external force in the x direction is 0, then the momentum in the x direction is conserved. So an example of this second special case here is projectile motion, where, as you all know, when an object is given some initial velocity, it undergoes projectile motion, as shown schematically in the dotted line here. And if we ignore air resistance, the force in the x direction is 0 newtons, and that means that P of x is constant. P of x is constant, of course, because V of x is constant, and P of x is just m times V of x. On the other hand, F of y, the force in the y direction, is minus mg, which is not 0, and that means that Py is not constant. In fact, the rate of change of Py with respect to time is the rate of change of m times Vy with respect to time, which is m times the rate of change of Vy with respect to time, which is m times Ay, and that, setting that equal to the net force minus mg, gives us Ay equal to minus g, as we know from previous work. Second example is, consider the case of an isolated system. Isolated system is one which has no force interaction with anything outside of itself. No external forces, in other words. Of an astronaut and the astronaut's capsule. And so let's imagine that the astronaut, in the initial condition here, here's the capsule, mass m sub c. Here's the astronaut, mass m sub a. And I should Actually, here I should say m sub a plus m sub w. This astronaut has a wrench on their body, and the astronaut is stranded from the space capsule. The tether has broken, connecting the two. And so the initial situation is one where everything is stationary and the x momentum along the what is shown to be the horizontal direction here is 0. The sum of the momentum of this plus that is equal to 0. So if the astronaut takes their wrench and throws it in the negative x direction, giving it a momentum of minus mw times v wrench, then by conservation of momentum, the astronaut will have an equal and opposite momentum in the positive direction given by m sub a v sub a. And that is because there's no external force on this system. There's only the force of the astronaut on the wrench throwing the wrench to the left, but then by Newton number 3 there is a force of the wrench on the astronaut to the right, but that force between the wrench and the astronaut and the wrench are internal forces, which because of Newton number 3 cancel, and for that reason momentum is conserved. And so we can then say that the final momentum in the x direction for this system is MAVA, this momentum vector to the right, minus MWVW, this momentum vector to the left, which is equal to 0. And we can now solve for V sub a as being equal to MW times VW over MA. Well, clearly the mass of the wrench is going to be much less than the mass of the astronaut, and so it's up to the astronaut to throw the wrench as hard as he or she can in order to gain a respectable velocity v sub a in the x direction.